All right. Hello, everyone. Thank you so much for being in the presentation today. Today, we'll be looking at the design and control perspectives on how to use reinforcement learning in built environments. So let's jump right in by looking at what a built environment is. And any of us living in an urban area, we are all too familiar with built environments. Is actually built environments are what makes any place urban, right? I mean, they have things like buildings, pedestrian facilities like sidewalks and crosswalks, transportation networks where people switch modes from commuting via foot to getting on a bus or things like that. And mainly in terms of the problem that we're looking at, I'd like to think of this as a multi-stakeholder perspective. As in, there are multiple stakeholders in a built environment. Primarily, they are things like vehicles, pedestrians, and designers and planners. And existing work, if we look at any transportation or even optimization venues, we'll see that existing work mostly focuses on research towards one particular stakeholder, that is vehicles, whereas every now and then we'll see some work trying to address the problems or optimizations related to pedestrians, whereas it's really hard to find any kind of a comprehensive study that targets planners and designers, which are also an important part of the whole stakeholders in a built environment. So, and also the other thing that we observe is that most of the frameworks that exist out there address them independently, as in they are not unified in addressing all the stakeholders in a built environment. And what we are trying to do here is try to address all possible stakeholders in our framework in a unified manner, which does not exist so far. So to address all these stakeholders, I mean, that's our motivation of this work, right? And in order to better understand how they have different objectives, and those objectives might be often competing, we have to kind of understand how the design and the control aspects are related to various stakeholders interact, and what are the trade-offs. And this is also kind of a motivation behind why we feel the necessity in optimizing these things, right? So imagine that we are in a place like this where we have two intersections that separate a block, and in the middle of this block there exists a building which is a pedestrian generator. And in order to save the cost, whatever a university or a city decided to not build a mid-block intersection. Now, how this affects, the designer, what they tried to do was try to optimize for or maximize for their cost. But in terms of other stakeholders, such as pedestrians, now have to go all the way to the end of the block in order to cross the road, and that kind of minimizes their travel time, right? And we all must have faced similar scenarios ourselves as well. And so the ideal solution here is to build something like a mid-block crosswalk that would minimize the travel time for the pedestrian, but it would increase the cost of initially building that crosswalk as well as later maintaining it. And one more thing, that the previous scenario where the pedestrians had to go all the way to the intersection, what this does is it not only increases the travel time of vehicles traveling east-west, because the pedestrians now have to cross, it also decreases the travel time of the vehicles going north-south, because now it has to accommodate for that pedestrian to cross, right? Whereas in this setup, what happens is the vehicles now, although the travel time for pedestrians is reduced, the vehicles have now to make more stops when going from one intersection to the other, right? So there are so this kind of a built environment is inherently kind of an environment where there's multiple interactions and multiple trade-off related to both the design and both control, and how these originate from various different stakeholders. So I made a nice little table here to try to see what are the different things that each stakeholder wants to optimize for. And for pedestrians and vehicles, actually safety is the biggest issue. And among other things, safety is also a function of design. I mean, there's this crazy statistic that there are almost 20 deaths per day in the United States just because of a pedestrian and vehicle clash, and this highlights kind of a lacking in the infrastructure that we have in this country. And for the planners or designers, one of the things that they want to maximize or minimize rather would be cost, whereas other things like reduction of the queue length, reduction of the wait time, reduction of the total travel time. I mean, there's sufficient literature out there that has already established the necessity of these things. And one of the other things that like the designers would want their control from the control perspective, the designers would want their systems such as traffic lights or signalized crosswalks to be real time and adaptive. For example, we have a big football game here in Knoxville every Sunday where the foot traffic at those days is like 50 times higher than the average day. And we would want our systems to be adaptive in such cases of spikes and peak demands as well. And in our specific context, the built environment that we are looking at is the Crever Road at UNCC. And here there exists an intersection at the very left end where there's a traffic light, as well as there are signalized crosswalks, meaning that people walk up to these crosswalks, wait for a certain time, and then they are serviced where they can cross the crosswalk and go to their destination. And this represents the control elements in our built environment that we are working with. Whereas for the design elements, we have 8 different unsignalized crosswalks, and these unsignalized crosswalks mean that neither the pedestrians nor the vehicles are commanded to stop or go. But whenever pedestrians try to cross, the vehicles give them the right of way. And when put together, it looks something like this, where we have a control element all the way to the end, and there are some design elements where these crosswalks, where they are placed, how thick they are, those things also come into play, and they have a certain interaction with each other, like we discussed earlier. And so our initial approach to solving both the design and control using reinforcement learning was to formulate this as a joint problem, and then joint optimization problem. And after a certain while, we realized that it was not a good choice to have a single agent solve both design and control, mostly because these two things operate at different time scales. As in, if you have one design, then you'd want to evaluate that design over a prolonged period of time, as well as over various different demands before you learn what to change about that design, right? So inherently, this is a hierarchical structure problem. And we also had some technical challenges, such as we had to now do these things like action and observation decoupling. We have to tell this specific agent that, hey, this is your action and this is your observation, and then things got really hand-wavy after that. So we formulate this problem as a bi-level hierarchical optimization problem where we have a design agent and we have a control agent. And in practice, it looks something like this, where we extract a pedestrian graph network from the existing real world, and then we feed it to the design agent, which proposes a new design iteratively. And then those designs proposed are taken by the control agent, which learns a control policy on those traffic light and the signalized crosswalks. And then based on the performance, they receive their rewards at different time scales. And of course, this is a very high level zoomed out, 30,000 feet view of how these things work. And we can take a little bit more in-depth look, but still still not going into the weeds of what are the MDP components and things like that. So just getting into a little bit more depth, we have a mechanism where the design agent takes the graph, and then it can output variable number of unsignalized crosswalks, and each unsignalized crosswalk can have their own location along the corridor as well as its own thickness. And this is done by using a Gaussian mixture model, and the location and thickness are also modeled as a joint distribution, and the neural network has a separate head that allows it to also choose how many times it can sample from this Gaussian mixture model. And this kind of is a reparameterization trick that we used, because under the standard purview of reinforcement learning, we're kind of forced to have fixed action size and observation size, but we want to give the agent the ability to propose. I mean, if for some reward function, if the best solution is to propose just one single crosswalk throughout the whole corridor, it has the ability to do that as well. So we wanted to make the agent more general and more flexible in what it can do. Hence, we chose something like that. And then the agent can propose new edges along the corridor. I don't know how much of it is visible here, but you can see that over here, yeah, I mean, these green colored ones are the ones that are proposed by the agent. And then we take the pedestrian network graph proposed by the agent, stitch it back with the sumo network, and then we parallelize those networks across different processors. And then in each of them, we simulate a different demand. We simulate a different demand. For example, the vehicle demand could be 0.5 times the original demand. From the real world, pedestrian could be 3.1 times. And then based on the performance within that same parallelization, the control agent receives its reward, whereas the design agent receives its reward as an average of, for example, things like total travel time or things like that across all possible demands. The design agent would then get that reward and propose a new design based on as a feedback. Based on the feedback. And so that was a little bit more into the depth. So in terms of coming back again into the hypothesis of why I expect this to work and why we think this is a good approach to this problem is fundamentally, the traditional way of making these design decisions on these built environments have been done in a heuristic way, as in traffic engineers, urban planners, they use these established heuristics, such as the distance from an intersection for a crosswalk should be 150 meters, and the distance between two consecutive crosswalks should be 100 meters, heuristics like that. But then heuristics can often fail us, and then we can often see examples where data-driven approaches perform better. And one really clear example that highlights this is that in this figure, this some designer proposed this design for a pedestrian pathway based on some heuristics, but kind of this is like a data-driven approach where the actual desired lines did not agree with the proposed design. And later, what the designers realized was that adding something like that based on what the pedestrians actually desired was a better choice. And and then such desired lines and where pedestrians accumulate, where pedestrians generate, may not be directly obvious to the designer during the design time. They can only be known at when the things are actually occurring in the real world. And in terms of the experiments, the hypothesis that we have currently is something like the design agent performance would be more pronounced at higher demands. These are just trend lines. These are not the actual experiment results. These are what we expect. And if we see here, towards the low demand, the metrics such as the total travel time for pedestrians and vehicles, we expect them to be low, whereas we expect them to be more pronounced at higher demands. Similarly, for the control agent, we expect, actually we already had some preliminary results on this, and we expect the wait time at the intersections as a function of control agents' decisions to be lower compared to traffic light. And in terms of the current status of the project, we have the control agent setup complete. We have the design agent setup complete, as well as the simulation setup where all the actions have to be applied, and then all the graphs have to be handled and passed along and whatnot. We have all those things complete, and currently we're looking at hyperparameter tuning, and shortly we'll begin our main training. And that's it for the presentation. I'm now open to any feedback or questions that you might have. Thank you.